We're on. Hello all, welcome to our third Michaelmas talk for Oxford Space and Astronomy Society. I'm Maruthi and I'll be hosting the talk today. Firstly, apologies for the connection issues last week. We're back today with our fantastic speaker, Professor Chris Lintott. Professor Chris Lintott is an astrophysicist at the Oxford Department of Physics. His current research involves investigating galaxy formations and exoplanets. He is the primary presenter of our beloved show BBC's Sky at Night and heads a number of well-known citizen science initiatives. Professor Lintott is a fellow of the Royal Astronomical Society and a legacy fellow of the American Astronomical Society. Chris, we're honored and humbled to have you here today. So without much further ado, over to you, Chris.
Excellent. Thank you very much for having me. Thank you, everyone, for joining us. I hope you're all safe and well, whether you're in Oxford or elsewhere. I'm going to try and give you a sense in the next 40 minutes or so of the state of play in what I think is probably the fastest moving area of science, bar none right now, which is our understanding and discovery of planets around stars other than the sun, something that in 20 years has gone from the kind of discovery that makes you a Nobel Prize to almost entirely routine. And so I think this is a good time to think about why we care about exoplanets and what all these discoveries might tell us. One way of thinking about where we are is that there are three phases of exoplanet science. The first, which lasted more or less until the discovery of the first convincing exoplanet candidates in the mid-90s, is the theoretical and speculative phase. Then there's a discovery phase, which probably lasted from 1995 till roughly now, where the main missions and progress has been made by large surveys attempting to tell us where planets are and how common they are. And I'll say a bit about that in a sec. And then a third phase, which I think is just getting started, which is an attempt to take all of the information that we now have and use it to understand in detail the processes by which physics and chemistry create planets and indeed created our solar system. So it's the fact that we're on that cusp that means I wanted to talk about this today. There are many people in Oxford better qualified than I to talk about this topic. So this is a sort of astronomer's non-expert view of what I'm going to call in my first slide, the exoplanet revolution. So I am assuming that you can now all see the first slide. If you can't, I assume somebody will tell me. One thing I want to start by emphasizing is that I'm going to tell what is essentially an observational story. If the revolution that we're talking about is the idea that most of the stars in a star field like this one, or indeed if you go out, it's beautifully clear in North Oxford this evening, if you go outside after the talk and look up, most of the stars that you see, we now know likely have planets around them. A good number of them have planets that might be at least a bit like our Earth. And that's sort of a revolution in thought. It turns what is otherwise a picture into a map of many potential worlds that we can set science fiction around or that we can imagine exploring one day. But that's not really a theoretical revolution. If you talk to a particular kind of grumpy theorist, they will tell you that surely the same physics and chemistry that formed our solar system must have operated throughout the galaxy and presumably in many other galaxies. And so we could have predicted that planets existed. But this is something that needed to be tested. and it's only been tested in the last few years. And really, you have to realize that's where I'm coming from as an observational astronomer. I get a kick out of novel observations of the universe. So just for fun, if we're talking about looking up at the sky, here's a pretty terrible shot of sunset. It's about the same level of twilight as it is outside. And if your monitor's good enough and my Zoom connection's working well, you might be able to see there's an evening star in the sky here. And if you go outside tonight and look east, you will actually see a similar view, except that if you zoom in here, this is a double star in this particular picture. So that should give away what we're looking at. This is in fact an image taken about 6 years ago now, not from Earth, but from the surface of Mars by one of NASA's rovers. So this is a sunset sky on Mars showing Earth and of course the moon as twin planets in the sky. So we can go out tonight and look at Mars. So by being on a different planet, we get a different view of Earth. And what the exoplanet revolution is doing for us is giving us that sense of Earth as a planet, as one of this community and population of planets within the Milky Way galaxy. So if I've asserted that there are planets orbiting almost all of these stars, I should be able to show you them, right? Well, I could do that for a few systems. So this is an image of a star called HR8799. Actually, it's almost exactly the opposite that. It's an image of everything but the star. So this is from an instrument called SPHERE on the Very Large Telescope, the European Southern Observatory's Very Large Telescope in Chile. And this is from an instrument called a coronagraph, which simulates the stellar equivalent of a solar eclipse, a total solar eclipse, that blocks out as much of the light from the star as possible. So that's doable in this case because the star is relatively faint. It's relatively nearby. It's just 130 light years away. But when you do that, you get these four blobs that are left. And over the course of many years, almost a decade, you see the date in the bottom left, those four blobs are revealed to be orbiting the star. So this is the equivalent of the animation that you've seen a million times of planets whipping around the sun, but in real data. And you can think of this as a sort of blown up version of our solar system. So these planets are sort of, the largest one's 2 to 3 times the size of Jupiter. The smallest of them is about 2 to 3 times the size of Neptune. The innermost orbit is 45 years. The outermost orbit is 460. So it's our 4 giant planets blown up and pushed out a bit. And that's why they're visible. They're quite a long way from the star. Now, in this case, I can show you the planets, but in most cases, as you probably know, the glare of the star prevents us imaging the planets. That's it's not that the planet's too faint in most cases, it's that the star's glare is too bright. The typical analogy is something like a glowworm flying in front of a stadium floodlight as seen from 3 miles away. So we find indirect methods to look. So one of those is the radial velocity method. Here's a distracting animation of a planet that may or may not exist around our nearest star, Proxima. This was discovered by a method called radial velocity. And here you look at the spectrum of the star and you use the lines, the spectral lines of the stellar spectrum, and you look for regular patterns where they shift redwood, then bluewood, then redwood, then bluewood. And that shift would indicate the star wobbling, or rather orbiting the common center of motion between the star and the planet. So that's a straightforward method. It requires exquisite precision. The typical velocity induced on the star by a planet, even a large planet that's close in, is of the order of kilometers per second. So you need to be able to measure the movement of a star, a distant star, to better than 1 kilometer per second resolution. But it can be done with modern instruments. And many of the planets that we know about were found this way. The only problem with this method, there are biases with all methods, but the real problem is that it's expensive. I have to take a look at a particular star that I'm interested in on night after night after night after night after night in order to get enough data to be able to detect this wobble. A problem made much worse by the fact you don't know the period of the planet, so you have to sample very frequently to be able to get data to rule in or out the presence of planets there. So we would most like for our middle phase, our exploration phase, is a method that allows us to capture many planets at once. This method exists. It's called the transit method, and it builds on an incredibly simple realization. I like when observational astronomy is built on simple foundations. So this is the sun. This is actually a video from the university parks of a day back in 2012 when Venus crossed in front of the sun. We had a transit of Venus. Maybe some of you, wherever you were able to see this. And on the left is the video, and on the right is the results, just sticking a lab multimeter out in the open air. And the incredible realization is that when Venus blocks out some of the light from the sun gets slightly fainter. That's the brightness that you see on the right there. And so you can imagine, now because of the way our orbit is inclined and Venus's orbit is inclined, we only have transits like this at most twice a century. But you can imagine if you happen to live in such a place in the galaxy that you happened to be in line with Venus's orbit, such that every time Venus completed an orbit, it caused one of these blinks, then that repeated pattern would tell you pretty quickly that a planet was present. And it would even let you deduce things about the planet. You get the size of the planet from how quickly the eclipse happens. You could also get the period because you get the time between the dips. And people have even started doing spectroscopy to understand the planet's atmosphere by comparing the stellar spectrum when the planet is not in the way to the spectrum received when the planet is there. So you use the star as a background light source to light up the planet. Now, the advantage of the transit method is that we can monitor many, many stars at once. And so the great advantage, although some has been done by the ground, from the ground, the exquisite photometry, the accuracy of the brightness of the measurement that's needed really pushes you to do this in space. And this was done by a mission called Kepler in particular, which monitored for the 3 years of its main mission, monitored 150,000 stars in a patch of sky in the constellations of Cygnus and Lyra, and measured their brightness. And then people could sort through and look for these transits, and they were able to find this result that really planets are very common. Obviously, most of the planets that exist in the Milky Way are inaccessible to us via this transit method. If the orbit is such that it doesn't cross the star as seen from Earth, we're never going to see that planet. But one can play with statistics. That's just a geometrical effect. And so you can extrapolate out from what you can see to work out what you can. It's worth saying in passing, I think, actually, that one of my favorite systems is Teegarden star. So Teegarden star is one of the nearest stars to the Earth. It's a dim red dwarf. It's about a tenth of the mass of the sun. So it's a puny little thing, really. And it's nearby. It's about 12 light years away. And we know that there are 2 planets going around it. They're known as B and C. We're not very good at naming this. This was announced a year or 2 ago. But what's intriguing about this system is that we know that they lie in line such that the plane of this solar system matches, by coincidence, the plane of our solar system. So if you had a hyper-advanced telescope in the Teegarden star system, you'd see the view of the solar system above. But the crucial thing is that if you were an astronomer on one of these planets and you had a telescope of the sophistication that we have now, you'd, in theory, be able to discover the whole solar system via this transit effect. So there are places in the universe where this coincidence plays out. So we've got direct imaging, we've got radial velocity, the wobble method, we've got transit photometry. There are a couple of other minor methods as well, but put all together, how are we doing? What's our scorecard on planets? Well, this was last week. I didn't update today, but this is the NASA scorecard. You can see there were 4,296 confirmed planets. One of them's getting its moment in the sun there on the right. And you can see that we've sort of started to classify them into sizes. So there are 4 sorts of planets that we should care about. We can think about rocky planets, terrestrial planets. In our solar system, that's Mercury, Venus, Earth, and Mars. You talk about gas giants, and that in the exoplanet context really means very big indeed. So that's Jupiter and Saturn. And then there's sort of Neptune-like worlds, so Neptune and Uranus. Often in our solar system, they're called ice giants for various reasons, so sort of intermediate. And then there's this category called super-Earth planets, which are likely to be the most common. And we use super-Earth because it sounds better than puny Neptune. But these are planets that sit between the rocky planets and the ice giants. They may have a radius of 2 or 3 times the size of the Earth. And I'll come back to that later. But it's kind of intriguing that the most common class of planet doesn't exist in our solar system, as far as we know. It's possible there's one of them lurking on the edge of the solar system, but assuming we've only got our 8 normal planets, we don't have the most common type. So this is a really clear example of the cosmic perspective that I'm talking about, putting Earth in context of these discoveries. Here's another view from the NASA exoplanet site. This shows you on the right that it is indeed the transit method that has discovered most of these planets. That makes sense. You're monitoring a lot of stars at once. But on the left, I think, is a diagram that I want to spend a little bit of time on. So this is sort of the fundamental plane of planets. So that on the y-axis here, we've got the planet mass in Earth masses. And on the y-axis, you've got the orbital period in days. So there are a few things to note about this. So the color of the dots tells you the discovery method. And what you can see here is that transiting planets tend to be closer in than those found by radial velocity. And that's simply an artifact of 2 things. One is the data. When you're monitoring the star's brightness, it's noisy, and you often require many dips, many transits to significantly infer the presence of a planet. The trouble is that as you go further out, you have to wait longer for that to happen. The more geometrically minded amongst you as well will have realized that the further I am as a planet from the star, the smaller the region of the galaxy from which the planet will transit. For a planet that's very close in, lots of observers at all solid angles will see it transit. Whereas as you get further out, the odds of getting lucky enough to be exactly in line with that orbit drop dramatically. So transiting planets are always going to be those closest to their star. Radial velocity has a bias as well. Bigger planets that are closer to their star make for bigger wobbles, but it's less significant. The other thing you can see from this diagram is that for a given period, we're more likely to find more massive planets. So that gap in the bottom right, where we're not finding, say, Earth mass planets with periods greater than about 100 days, we think, for various reasons, that's just a systematic. And we'll talk about that later. But what everyone really wants to do with this diagram is put Earth on it. So here's an earlier version. This is from just from Kepler now, just because it's the diagram I happen to have with me. And that is the radius in Earth radii. So we've gone to radius rather than mass. There's a slight subtlety here in that the transit method gives you the radius. The radial velocity method, the wobble, gives you the mass of the planet. So if you've got both, you know everything about the planet to first order. If you've only got one, you need to model the planet to infer. But these are just transiting planets. And the large dots in the bottom right are Mercury, Venus, Earth, and Mars. And so you can see that the planets of our solar system live in a relatively unexplored area of the parameter space. But we know that this is down to the kind of transit biases. So this talk was radically updated last week when a new paper by a lot of the Kepler team came out, predicting for the first time their final numbers on what they call eta Earth. So eta Earth is, to first of all, the frequency with which sun-like stars have Earth-like planets. Now, I need to define Earth-like. That term causes shudders throughout the scientific community. because for much of the period in which we've been discovering lots and lots of planets, people have gained press attention, and people have got scientifically excited about planets because they're Earth-like. And that has been a relatively shifting term, for example. So, for example, Earth-sized is not the same as Earth-like. Venus is Earth-sized, but you would be upset if I moved you rapidly to Venus. Life may not cope very well. Although recent discoveries, which I'm happy to answer questions about if you want to ask, might have said something about that. There's also the case that if you took Earth's atmosphere away, the temperature on the surface of our planet would be very different. So just because you know that there is an Earth-sized planet and an appropriate distance from the star to have to possibly be able to sustain reasonable life supporting temperatures, whatever they may be, doesn't mean that a particular planet that we found will actually have such conditions. And so I want to introduce you. So there's an old idea of what's called the habitable zone. It used to be called the Goldilocks zone, which is around any given star. The habitable zone, or Goldilocks zone, is the region where the temperature is not too hot and not too cold, but where the temperature is just right usually for liquid water to exist, with the idea being that liquid water is an essential ingredient for life. I think I want to be a bit more specific about that. So we're going to talk about what my friend Jesse Christensen from Caltech calls the, I don't think we've decided how to pronounce this yet, Exoplanet, I guess, zone. This is a still from a video from Elizabeth Tasker, who works for the Japanese Space Agency. I highly recommend her video. The three of us decided that Exoplanet is probably an obscure river god, but what it actually stands for is Earth could have liquid water on the surface. So the Exoplanet zone is the zone around a star where if you transported Earth to that position, an Earth-sized planet with our atmosphere could have, doesn't necessarily, but could have liquid water on the surface. So this is then a perfectly sensible scientific thing that one can think about, and that's what this paper from Jesse and the rest of the Kepler team does. This is a slightly strange figure, and I'm not going to go into it in detail. The x-axis, so the y-axis is what we'd be dealing with. This is just planet radius, derived from the transits. And on the x-axis, this is the now not the period with which the planet goes around the star, but this is the amount of heat, essentially, that the planet gets from the star. One is the same as Earth does around the sun here. So that black cross at 1, 1 is the Earth. What you can see, what I want you to look at really is the color, the blue to pale blue that washes from top left to bottom right. That's the predicted completeness of the Kepler population of planets at that point in this space. So we would only have found, at the point where Earth is, we would only have found one in 1,000 Earth-like planets. So if we find any at all, we should take very seriously the idea that there's a large population there. And if I go back to this diagram, you can see that there is sort of 1 or 2 or 3 points down in that bottom right corner. And so when you take the sparse understanding we have of the planets that exist in that part of the diagram and this complex, difficult calculation on completeness, then the two, you multiply a small number of planets by a large correction, you get a number that between about 40 to 60% of sun-like stars have a rocky planet in the Exoplanet zone. So these are planets that might be potential places for life. So that means that there are 5 billion Earth-like planets, if I go back to the old terminology, in the Milky Way alone. And that's now a number with an error bar. So if any of you are fans of Carl Sagan's Billions and Billions of Worlds, we now know the number. It's somewhere between, say, 4 and 6 billion Earth-like planets in the galaxy. What's also exciting about that number is that I think it's a bit higher than most people would have estimated. In fact, I know it's a bit higher than most people estimated. So nature's clearly good at producing these kind of planets, but it also is important for a big argument that's going on right now in astronomy, which is that we're trying to decide, or actually more specifically, right now, the Americans are trying to decide. They're trying to decide many things right now, but there is a process by which NASA and the American funding agencies, the National Science Foundation in particular, every 10 years consult the whole astronomical community to identify priorities and big projects for the next decade. And these decadal surveys set the tone for world astronomy. The US still funds a lot of the hardware, although not all of it. Anyway, for this round, this is happening now, there was a particular focus on the next generation of space telescopes. And there are 4 things submitted. So this would be not James Webb, which is about to launch and investigate the first galaxies, which will do great exoplanet science. But these are telescopes that might launch in the 2030s if we're lucky, and the 2040s more realistically. And my favorite candidate is something called LUVOIR, the Large Ultraviolet Optical Infrared Space Telescope. It'll need a better name if we launch it. As conceived at the top here, this is a 15-meter mirror with a large sunshade. And to give you some idea of the capability, on the right, for example, that's Hubble's view of Pluto in the bottom right, and at the top is what LUVOIR would see. And actually, the resolution's not far off what we got from all but the closest flyby images from New Horizons. The point is that now we know Eta Earth, we can predict, and there's a galaxy example on the left, but we can predict how many of those Escher-Watt zone planets LUVOIR will be able to take spectra of. And the answer is 54. So that number, being big, is good. And you might be able to do this kind of thing. So these are the spectral energy distributions for different types of planet. And so you could see here, just looking at the bottom left, that LUVOIR for each of those 50 or so planets would be able to distinguish a Venus from an Earth, and an Earth in its present state from an early Earth that maybe is less affected by biology. And so if you want to try and work out how many actual Earth-like planets there are, then you're going to need something like LUVOIR, but we also need that number to be high. So the fact that there are lots of Earth-like planets is very good news. And actually, you could start to work out what the odds are. So you can ask the question, we don't know the percentage of planets that are actually Earth-like in the sense that they have our kind of atmosphere. How many do you have to look at to be able to find one? And if we have 50 candidates, if only 5% of candidates are Earth-like, then we can actually go and find something. So EchoWatts, I think. So I think this is a really important set of calculations that's come out of an awful lot of detailed work looking at the Kepler data and the other descriptions. Of course, that doesn't mean we're going to go and find aliens. This might be a way off yet, but we shall see. And of course, just because you found an Earth, maybe other things are critical for life. So maybe you need a moon. We don't know about exomoons yet, and maybe life wouldn't get started, and so on and so forth. But we're at the start of this really, really exciting adventure of being able to actually study nearby Earth-like planets. I could talk for the remaining 15 minutes of the talk about that and about that adventure, but I want to switch gears a second and talk about a parable. So this is another image of Mars. This is one taken from the Mars Reconnaissance Orbiter with its high-rise camera. And the most interesting thing in this image, probably, is this dot that I've just drawn a circle around, because that dot is one of the Mars rovers. We've now got to a point where we can see a rover on another planet. So this is taken by an orbiting spacecraft, but that's quite fun. This one, I think, is Opportunity, one of 2 so-called MER rovers that operated from 2000 until just recently in the case of Opportunity. And the principal investigator for that mission is this guy, Steve Squires, seen here celebrating the successful landing of Spirit on the red planet. I was lucky enough to talk to Steve about a year into the mission. And the goal of these rovers was to find evidence for past water on the Martian surface, because NASA's goal in going to Mars is to determine its current and future habitability. At the time I talked to Steve, Spirit had managed to discover that there had likely been water on the surface, but not the kind of water that you would want to drink. It had found evidence in the mineralogy for extremely acidic ancient water. Now, later on, we would find evidence of pH neutral water on the once flowed on the Martian surface, but at the time that wasn't true. And I mentioned to Steve that I was pretty disappointed that that if Mars had been an acidic world in the past, that presumably did bad things for life, and it was a bit disappointing. And the man was tired. He'd been running a mission that was supposed to last for 90 days for several years, and he reacted pretty angrily. And he said to me, "Look, we don't go to Mars because it looks like Earth. If you want to understand Earth, you'll have a much better job with a hammer out in the field here. You don't send a robot to Mars to understand your backyard. You go to Mars in the hope that you find that it's Mars-like, because then it tells you a different story." And so every one of these planets, it's very easy to get sucked into this search for our own counterpart and our search for alien life, which is one of the great adventures of human history. But we should remember that every one of these planets has its own story to tell. And that when we look at the space and we start to split up this diagram, we can find out fantastic things. Some of my favorite planets are those in the bottom left of this diagram. They're Earth-sized worlds that go around their stars in just a day or two. These are lava worlds. They're probably rocky, but their surface will have melted. This is an artist's impression of a place called Crow 7b, which is about as close to hell as I think we found. It's a sun-like star, a bit bigger than the sun. It's a 5 Earth mass planet, and it's small. It's only about 2 times the size of the Earth. So it's a dense Earth. So it's rocky, but it's probably tidally locked, so it keeps the same face to its star, and it's melted. We didn't know planets like this exist. We want to understand how it's formed, how it's endured, what it's made of, why is it dense? Has it always been there? What will it evolve into? These are all new questions that we didn't know to ask until we found Corot 7b. One possibility is that it used to be a much grander planet. This is an artist, I'm sorry about the artist's impressions, but as I said, we don't have pictures of these things yet. This is an artist's impression of HD 209458b, which is 4 million miles from its star. This is a Jupiter-sized planet that probably has the good claim to be the largest comet that we know of, because its atmosphere is boiling away as we speak. And certainly in a billion years' time, this will have no atmosphere left. And what you might be left with is the rocky core. So Corot 7b might be a naked core of a previously gas giant planet. The fact that this planet existed, in fact, that any hot Jupiters in the top left exist here. These were the first planets to be found. They were a surprise because in our solar system, Jupiter and the large planets live further out. They're cold gas giants. The fact that hot Jupiters exist tells us, we think, that planets migrate in the early system, that they move around. And this is a story that people had sort of got to a little in advance, but which is being really punched out now. So let's talk about that. Let's talk about planet formation. So just to remind you, this is, I keep meaning to replace this graphic. This is a NASA graphic that purports to show the arrangement of our solar system. Yes, Pluto is not a real planet. We can fight about that later. But Mercury, Earth, Venus, Mars, Mercury, Venus, Earth, Mars, rocky planets close to their star, Jupiter, Saturn, Uranus, Neptune. Big planets further away. This we thought was a fundamental rule of planetary evolution. And we think we know why that is. We had 400 years to think about it. By the way, the reason I hate this graphic is that you have to ask yourself where the light is coming from, if that's the star on the left, but never mind. so we know about planet formation. We know it happens in places like this. This is the Orion Nebula, our nearest big star forming region. And in the blobs at the center that you can see here, planets are forming. If we zoom in, is this going to work? Yeah, so this is now an animated zoom from a telescopic view of Orion. This is a 3D version. You can see there's bright stars that have just formed embedded in the nebula that light it up. But you can see these little tadpole-like things around those stars. They're known as propylids, and they are stars that are just being born. So these are stars with the remnants of material around them, and that material forms a disk of material, as we'll see in this slightly strange animation. So there you go. So you end up with a disk of material at right angles to the star's axis of rotation. You sometimes get jets, which is what we've shown here. But from that disk of material, you can get planets to form and build up. So here is now quite an old but rather nice explanation of what happens. So we will simulate the disk with a bucket of water. So the disk is rotating. So we've just set that in motion. And then we're going to sprinkle in some dust. In this case, it's pepper. But what you can see is it's quite hard to see to begin with. And then the pepper becomes more obvious because as the pepper grains move in the rotation of the disk, they begin to collide and stick together. So we think that in a protoplanetary disk, planets grow by sticking together. And that makes sense. Most dust grains have icy mantles. So when they collide, they're sticky. And you can build up bigger and bigger things. There is, however, a bit of a mystery in the solar system. And the mystery is that we don't really understand how to get, there's a size scale that we don't know how to jump over. So when you collide two dust grains together, especially if they've got a bit of ice, they will stick together. They will then stick to the next thing they collide with, and so on and so on. You can build up something that's about the size of a car, or maybe even something a kilometer across pretty easily. But at that point, there's a regime where when I collide two objects that are that size at any particular speed, you're more likely to end up with rubble than you are with a new thing that's twice the size of the car that you started with. Gravity at that scale is not strong enough to hold rubble piles together, and the chemical forces that attach smaller dust grains together aren't strong enough to do that either. So you end up, we don't really know how to bridge this gap. And I wanted to mention in passing this thing. This is Oumuamua, which was the first interstellar object seen flying through the solar system. Oumuamua is this bizarrely shaped asteroid which came flying through the system. And it turns out that there are untold numbers of such things in the galaxy, we think. At any given time, there's one rock that's a few hundred meters in size flying through our solar system inside the orbit of Neptune. And so my friend Michelle Bannister, who's in New Zealand, believes that these things seed planet formation, that you have a disk of dust and then you throw in a few of these and they become nuclei around which planets grow. And if that's right, then our planet might have started as an interstellar visitor to this system, which I think is both a brilliant and slightly poetic idea. Anyway, I was trying to explain that why we think giant planets form further out. So we clumped out our stuff together, but exactly what clumps will depend on where you are. When you're close to the star, you're warm and there won't be much gas about. So you grow a nice rocky core like the Earth or Mars, and then you'll stop. Further out, it's colder, hydrogen gas can be present, and as soon as you grow to be about the size of Mars, you quickly grow an envelope of gas. So that makes sense. So we think that different planets form in different ways, and we're even getting some of the detail of that. It's now pretty clear, and this is Kepler results, that small planets come in two sizes. So I've already hinted at this because I talked about terrestrial planets maybe no bigger than 1.5 times the size of the Earth, and super Earths, which are 2 or 3 times the size of the Earth. But that valley in between them in this frequency graph is real. So there's not much in between. And so you're either one thing or another, and it's to do with, we think, how quickly you assemble. So here's what the family tree of planets looks like. I seem to have lost the ability to control this. Why have I done that? Hang on. There we go. So you have your protoplanetary disk. If you're in the outskirts, you grow quickly to be a giant planet because there's lots of hydrogen around. If you're further in, you're either going to be a super Earth or a mini Neptune. And what's happening is that you're essentially in a race against time until the star becomes hot enough to drive out the material from the center of the disk. So if you get big enough that you can grow your atmosphere in the inner solar system before the star switches on, then you can become a mini Neptune. Whereas if you're even slightly smaller, the atmosphere will grow slowly and then you'll lose it when the star switches on, just as the Earth has lost all its hydrogen. So the details of the planetary formation process are being elucidated by looking at the population of planets that we see. It's also true that we need to explain those hot Jupiters. So we think migration within the disk has become incredibly important. So it's now believed, rather than planets forming and staying where they are, that in the early days when the disk is thick, just friction between the planet and the disk from which it formed can allow planets, particularly large planets, to migrate inwards. So those hot Jupiters must have started further out. Then the question is why our Jupiter and Saturn didn't migrate inwards. And one answer might be that there's two of them. And because there were two, they quickly used up the gas in the disk. There are still some fun systems to explain. If this theory is right, and I think it is, then the Kepler-20 system is intriguing. This is a 5-planet system with a Uranus-style planet, a Mars-sized planet, a Neptune-sized planet, a Venus-sized planet, and then another Uranus-sized planet in that orbit, all close to their star, close enough that at least the 3 big planets, and probably all 5, have had to migrate inwards. But we think that E and F, the 2 small planets, will have formed closer to their star than B, C, and D. And so a decent explanation of how B, C, and D migrated inwards and leapfrogged E and F remains to be seen. And there is a whole set of model after model after model needed for planetary system after planetary system after planetary system, so we can pin down the details of these systems. What that means, though, is we need to go back and find as many as possible. And in particular, if I come back to this graph, we want to be able to push out to the right. So we want to find smaller planets in longer period orbits, because that's a region that we haven't explored yet. We wouldn't have found Jupiter, for example, using current methods. So we can make some progress by being smarter with the data. I run a set of citizen science projects, including one monitored by my PhD student, Nora Eisner, called Planet Hunters. Planet Hunters is now using data from Kepler's successor spacecraft, TESS, which is looking for planets around nearby stars. And Planet Hunters has been hugely successful at finding long period transiting planets. So we have hundreds of thousands of volunteers inspecting the data, and it's easier for them to find single dips than it is to find those things with algorithms. And so we've been very successful at pushing this graph to the right and finding planets that are missed by other means. There are also new missions coming up, which will help do that, and data from a satellite called Gaia, which will look for planets in a completely new way. So part of the frontier is completing this ladder, completing the task of working out what kind of planets are out there and what that tells us about our story about planet formation and evolution. The other part is that new instruments coming online will really enable us to characterize the planets that we're seeing. So I talked about LUVOIR already. That's a while away. But this is a visualization of something called the Extremely Large Telescope. This is the Extremely Large Telescope, which is being built by a European and worldwide consortium. So its mirror is 39 meters across. You can just see people down in the bottom right. And the enclosure for this is essentially the size of a sports stadium. So we're building one of the instruments called Harmony here in Oxford. But the ELT will be able to get spectral features in very nearby planets. It might not be brilliant for Earth-sized planets around sun-like stars, but it's certainly for planets around nearby brown dwarfs or red dwarfs. The ELT will enable us to follow up and really get an understanding of the atmospheres of planets, so that we can add to all of these diagrams, so that we don't just talk about bulk properties, but we can begin to understand what kind of atmospheres live everywhere. So I hope that's been interesting. I've given you a sort of ramble through what I think is a really exciting area. I'm going to finish by putting up our planet again. This is Earth as it drifts across the field of view of Kepler. And I think this image is just a reminder that in exploring and looking at these other worlds, we're finding out about our own place in the universe as well. And in both directions, there are plenty of mysteries and discoveries still to come. So thanks for listening. Hopefully there are questions, and I'll be happy to chat for as long as you like, really.
First of all, thank you, Chris, for that fascinating talk, just going through all the different exoplanet styles and everything. It's sort of mind-boggling to think about all of these things all put together. Again, once again, thank you for this amazing talk. I'll get started with a few questions. So one of the questions which we got was, how much time would it take to measure the only necessary parameters to consider it Earth-like? So maybe the atmosphere, the size, the core, and the orbit distance.
So time, I guess that's kind of a difficult question, but yeah, I think that stepping through it is the right way to think about it. So we get the orbit when we discover it, because you know a period. I am assuming, by the way, that we know about the star. So one of the paradoxes of this field is that what we know about the planet is often limited by what we know about the stars. So you do sort of need to know the stellar parameters, but let's assume the stellar astronomers have done their job and we've got distances and things like that. So we've got orbit, we get radius, and let's say it's a planet where we've got both transit and radial velocity. So then we get mass and radius. So we begin to get excited that this is really Earth 2.0. Yeah. Atmospheres next. At the minute, with present instrumentation for an Earth-like planet in the Escherichia zone around a sun-like star, we can't do anything with the atmosphere. We're going to need a big space telescope like LUVOIR. People get more excited by planets around red dwarfs or brown dwarfs, small stars, because the zone is much closer to the star, because the star is punier. And so that means that the transit signal is larger, so you've got a better chance. And James Webb, the next generation space telescope, should give us decent ideas of atmospheres of Earth-sized, a few Earth-sized planets around those stars. Okay. But then you can keep adding your list, right? So let's say I know it's got a thick atmosphere, and let's say we know that there's water in that atmosphere. That might make sense, but you might want to know whether there's land. So for that, you sort of want to do, I think you could try and do something with transit photometry, where you look for variations over time. Another big one that's quite fun to think about is that people have argued, Steve Bulbus, who's in the department, who you should have come and talk on this stuff, has argued that it's the presence of the moon that makes the Earth a decent place for life. So tides are important, he says. And our moon is unusual in the solar system. We're the only double planet. Again, Pluto is not a planet, but where we have a large moon. And I'm just going to keep saying Pluto's not a planet till somebody fights me about it. But so moons are important. We found one maybe exomoon, which is a Neptune-sized moon going around a Jupiter-sized planet, which doesn't really count. And in fact, that candidate exomoon is large enough that it could have moons of its own, which would be known as moons, which is fun. But so then you want moons, and then you might want to make sure that it's not tidally locked to its star, so you want to keep it rotating. Anyway, so the list goes on, but we will begin to have a decent list of candidates for very Earth-like planets in the next few years.
Okay, so sort of continuing on, what are the three biggest research questions, let's say, about the exoplanet study field?
Oh, well, I've gone through some of them. I think things I would like to know. I mean, the whole field is exciting, but I think we need to confirm that planets in sort of Jupiter-sized orbits are real. Everyone's making the assumption that that's true, but we don't know yet. So we need an intense study on longer period planets to sort of connect this up and to do the. I'd love to know if we've done Eta Earth. I want to do Eta Jupiter, because again, going back to the Earth-like question, that's interesting from planet formation, right? Do most Jupiters become hot Jupiters, or do most of them stay where they are, or both? We don't know. It's also interesting if you're interested in the life question, because one argument that's been made is that you can have a very habitable Earth, but if you don't have Jupiter in the solar system, then the frequency with which Earth gets hit by large comets and asteroids goes up dramatically. If you're a new comet in our solar system, the most likely thing to happen to you is to be slung out. The second most likely thing to happen to you is to you have an encounter with Jupiter, and that really matters. So that's one, long period planets. Two is atmospheres in general. So and we've got a space. I haven't even mentioned we've got a space mission coming. So there's a UK-led European Space Agency mission called Ariel that is going to do atmospheric follow-up for planets. So just understanding the diversity of atmospheres. And then I think the third one, normally people would say life, but let's leave that to the astrobiologists. I think the third thing is that we're beginning to create a catalogue of weird and wonderful things. So I didn't really talk about this at all, but we have circum-binary planets, for example, where you have a binary star and a planet going around both stars. We have planetary systems where it's possible that not all the planets are in the same plane. So you might have two episodes of planet formation. There's a lovely idea that you can have a planet that orbits one star in a binary system, and then every 10,000 years or so goes around and orbits the other one. We haven't found any of those yet, but they might be there. So I think the exotica is where I'd be putting a lot of my observational effort, right? Where I am putting a lot of my observational effort, because those, I said every planet has its own story. I want to hear the unusual stories, because often there's a lot of insight to be gained by trying to explain the really unusual things. And Planet Hunters is finding some really complicated. So poor Nora is spending all of her time trying to think hard about confusing data about a few systems that make no sense given what we can see so far. So that's part of the fun.
Yeah, that's wonderful. So again, so you said the sort of, what are the base? You said that there could be these objects which can be sort of planet-forming nebulae, or sort of the nucleus. What are the reasons behind conjecturing that such interstellar objects to be seedlings of planets, and where do they even come from? Are they sort of past solar systems which have been destroyed and are sort of flying through?
Right. So yeah, I find them fascinating. It's a topic I've started working on just because I think they're interesting. So the idea is, so you have to form some planets to begin with, right? So planet formation, in this picture, planet formation without seeding is hard. And by the way, just so people know, this is like not even cutting edge paper. This is sort of the cutting edge of the cutting edge. So everything I'm about to say might be wrong. So the idea is you form some planets somehow. And then, but an early part, it turns out that what happens in a world in which planets are migrating through the disk is that many of these planets many of the planetesimals, the small rocky things, are sent out into interstellar space. So we think, for good reasons, that the Kuiper belt, the region of rubble around Pluto, used to be about 1,000 times denser than it is now. So in other words, if you were born as a 1 kilometer sized rock in the Kuiper belt, the odds of you staying there throughout the solar system's history is about 1 in 1,000. And most of the rest end up sent out to wander through interstellar space. So that's why we think there's this background population. We've now seen 2 of them, and astronomers can extrapolate from 2 objects. So that's fine. Well, actually, there's a telescope, big survey telescope being built called the Vera Rubin Observatory that in its first year will test this idea. Amongst many other things. So that's the idea that they're wandering through, and that if you can get them to encounter, if there are enough of them, then the odds of them encountering a planetary system in the formation are high, and getting captured by the disk looks plausible. So that's the idea. Whether it's true or not, we don't know yet. We're busy working on it. But I think it gives you the idea that everything is connected. It also links to this idea of this chaotic early solar system. Most of them would be expelled early in the solar system's history. So looking at craters on the moon, although this is slightly controversial as well, the idea is that most of the craters on the moon were formed during a period called the Late Heavy Bombardment, just about 1 billion years after the formation of the solar system. It may be that was associated with Jupiter and Saturn suddenly migrating, disrupting the Kuiper belt and sending most of it flying.
Right. So I know you spoke about sort of this disk of planet forming sort of ooze, let's say, but we need this disk essentially to be perfectly aligned with our current solar system, or that in that angle for us to be able to actually capture the planets. So there could be
through the transit method, yeah.
Through the transit method, there could be quite a lot of planets which are obviously sort of perpendicular to this, to where our transit method could work. Is there a way to potentially find those planets through reflection?
So you could, as long as they're not completely perpendicular, you could still do radial velocity. So you could still look for the wobble, because the star will move like this or like this. If it's exactly perpendicular, it's difficult if you can't do direct imaging. But no, you can get them by other means, by radial velocity, and people have checked that the frequency with which we're making radial velocity discoveries matches what you'd expect from transit. So we think that all sticks together. If you care about a particular star, because it's a nearby star, you should go and do radial velocity. If you want a census of planets, then you do the transit method, because you can look for at many stars at once. If you look at enough stars, it doesn't matter that the odds are 1 in 100. Now, both of these methods get tricky as you get further out. I said that a few times. So then you either need to go to sort of direct imaging, or there are some other ideas. So Gaia, which I mentioned, is a satellite that very accurately measures the positions and velocities of about 1 billion stars. And in the next release of data from Gaia, we're expecting tracks of how some of those stars have moved over time. And we hope that some of those stars will be seen to oscillate as they move through the galaxy. And so you're literally not detecting the wobble via spectral lines, but you're literally seeing the perturbation of the planet on the star's motion. So that will be a plausible test. You can also look for lensing of gravitational lensing of background stars by planets. So micro lensing helps as well. And both of those methods are independent of the distance, or the second method is independent of the distance. So that'll help fill that in, but it's going to be a bit of a slog, I think. The other option is just do transit photometry on more stars, because you get more lucky. If you buy more lottery tickets, you win more often.
Yes, of course. So one of the are exoplanets the primary searching ground for, let's say, this is sort of astrobiology and sort of science fiction-y, but are they sort of exoplanets the searching ground for extraterrestrial life, and if so, why?
I think it's an odds game, right? So I think that certainly if you want to find intelligent life, which we know there's none in our solar system, so you want to look elsewhere. And I think one way to think about this in the context of SETI and the search for extraterrestrial life is people will know, I suspect, the Drake equation, which is this way of quantifying uncertainty in the number of civilizations that we could talk to. And the way to think about the Drake equation is not to get hung up on the numbers, but the first set of terms in the Drake equation are things like the number of stars in the galaxy that have planets, the number of those planets that are like Earth. There are astronomical terms. So I think where we've got to is we've shown that if aliens are absent, it's not the astronomers' fault, right? There are 5 billion Earth-like planets, right? So then the next set of terms are the biological ones. If you have an Earth-like planet in the equiwatt zone, will life get started? If life gets started, will it become intelligent? Both of those things are completely unknown quantities, which is why you shouldn't get hung up on the numbers, because you can multiply it by whatever you want. So it's the astrobiology we need to understand. we can have some input with atmospheres, right? I think if we looked at a nearby planet and we saw that it was Earth-like, and we saw that its atmosphere had oxygen in it, or other they're called biomarkers, gases that you think might come from life. I think the focus on those worlds would be intense, and we try and check that it's biology. If we still don't hear from aliens and the biologists solve that problem, then it's sort of a sociological problem at that point. It's why aren't they talking to us? Or why does civilization not exist? But so that's where we are in that path, and we're at this point where we're shifting from it being an astronomical problem to a biological one. But it's going to be very difficult to look at an exoplanet and say that there's life there. People may have followed the controversy and debate about phosphine on Venus. It's supposed to be a biomarker. It's a gas that on Earth is produced by biology. It was announced by a team from Cardiff and elsewhere to be in the upper atmosphere of Venus. And it's caused an enormous and rather wonderful scientific argument, which is still going on. But if people can't agree whether they could see that gas in the atmosphere of Venus, which is there next door, trying to do that from a distance of even 12 light years is going to be pretty tough.
Of course. Could you discuss a little bit more about the sort of citizen science initiatives? How do they work? How can we get involved?
Sure. So this is really what I do for a living, is run projects that invite the public to sort through astronomical data in a reasonably systematic way. I started off doing galaxies, so it's a project called Galaxy Zoo. Planet Hunters was an early spin-off project that used data from Kepler. So what people are doing when they log onto the site is they look at the light curves, they look at brightness over time, and we try and identify these dips. And if you've got an idle 20 minutes, you can log on and it's quite easy to flick through and start to get your eye in. We've got some simulated planets in there, so you can see how you're doing. And genuinely, we find hundreds of candidates that are missed by other methods. So if you want to discover a planet, you spend enough time on Planet Hunters, you will contribute, and the odds aren't bad. One of our developers found a planet because he was busy using his own project, which was quite fun. So that works. The other thing that Planet Hunters is very good at doing is finding the really unusual stuff, especially if anyone watching wants to get more involved in research and has a little bit of coding skill or isn't too worried by data analysis. There's a bunch of people who hang out on the Planet Hunters forum, look for when other people find interesting stuff and do follow up, go and get more data from NASA or do the standard checks that we do. If anyone wants to get involved with that, they can either dive into the forum or if somebody sends me a message on Twitter, I can happily talk about it. We really need people to do that because there's an awful lot to be found amongst those unusual and interesting things.
So just sort of one final question, a bit more academic, let's say, for young researchers who are just setting out their career in sort of wider astrophysics. What advice would you give them to shape their research in terms of focus and where to go? Or
I think I'd tell them to not worry about focus or where to go. Okay. And let me explain on that. So I think it's very easy to try and pick the hot field, right? To try and decide that you're going to want to. I'm going to do Exoplanet. It often comes up in Oxford because people have to do a fourth-year project, and people aim for the fourth-year project because they think that if I do that in this field, then I get a PhD in that field, and then I'll do that. And sometimes that works out, right? And you could see where data is coming in 5 years' time or whatever. So but astrophysics and scientific research in general is a set of skills. And one of the great joys of being a researcher, as an MPhil student, as a PhD, is the ability to wander slightly and follow ideas. So I think the thing to do is to pick projects to work on where you like the people you're working with and their style suits you. That's much more important than the topic. But also, I think it's always good to have in the back in your mind, why now? Why do this now? Like, is there fresh data? Is it a new question? Is there some reason to want to know this now? Those are usually the good signs of a good problem, right? Because that you know that you're then doing something interesting. So concentrate on people you want to work with and the why now question instead of trying to predict what all of astrophysics will be excited about in 10 years' time. a big industry right now is following up on things called fast radio bursts, which are these intense bursts that appear to come mostly from distant galaxies, although there was one announced in the Milky Way that sometimes repeat that we don't understand. And they were found by accident about a decade ago. And now, I think a third of astronomy jobs last year some involved radio transients. So the field shifts, and if you've got skills, you can jump about and follow it. If you've concentrated on always doing the same thing, then you're in some sort of trouble.
Thank you, Chris, for answering all of those sort of questions and giving us all the details as to how to learn more about and give us a bit more detail about this topic. Thank you so much again for all the viewers who've joined us in our live. I hope you had enjoyed the talk as much as I have, for sure. Thank you again, and hopefully see you all in the next talk.